Alrighty. For once, it's not staggered. And we begin a new one now. Last time we talked about the indefinite integral, and we talked about the net change theorem. Now we're going to talk about integration by substitution. Okay, as promised, we're going to talk about how to reverse the chain rule. We're going to talk about a substitution or a change of variable. And we're going to talk about how to do definite and indefinite integration by that method. Start with indefinite. Indefinite integration, or anti-differentiation by substitution. Okay, finding definite integrals is important in the real world. You want to solve problems, you want to calculate them. We've seen examples of that here. Thanks to the fundamental theorem, you can calculate definite integrals in many cases by finding the antiderivative, evaluating the antiderivative at the endpoints, subtracting, and there's your answer. So antiderivatives are important, and last class we saw some terminology and some new notation that's suggestive for dealing with them. What I also said was that while we have recipes for differentiating things, so whenever we have a reasonably dignified function, we can differentiate it, we don't have a general catch-all recipe for anti-differentiation. And in fact, some would say most respectable functions don't have respectable antiderivatives. For those that do, there is a recipe, an insane recipe, that I've read takes 100 pages to write out, that computer algebra systems can do. Obviously, that's no use to us here. Okay. Lesson is, there's not always a catch-all recipe, or there isn't a catch-all recipe for integration. Okay, so far, when we wanted to find antiderivatives, what did we do? We've broken up sums of differences, and we pulled out constants, and that breaks up our problem into bite-sized pieces. And we've been able to recognize functions that we know are derivatives of simple functions, and that's let us anti-differentiate things. And we've also added a few tricks here and there. For instance, we've corrected for factors we didn't want. We've used trig identities sparingly. And that's about it. And today we're going to use a new method. So we're going to learn how to reverse the chain rule, and that's going to let us anti-differentiate stuff that we couldn't anti-differentiate before. Okay. Recall the chain rule. Incidentally, there are other techniques for anti-differentiation. We won't learn them here for obvious reasons. If you want to learn more about them, take 128, see a textbook, see the internet, or talk to me. Okay, chain rule.
I think your microphone tires.
Well, here's the problem. You see, it's dying. Give me a second. This is an interesting time to be quiet. Thank you. Okay. What's the chain rule for? It's for differentiating a composition, a function of a function. A function of a function. So what do we do? Derivative of outside, evaluated at inside, times derivative of inside. Okay, this translates to Like all differentiation formulas, if we read them backwards, we get an anti-differentiation formula. So we can get this. Ridiculous font size today. Okay, easy peasy, you read it backward. So if your integrand looks like this, you're good. And you can write something like that, which is a big if. Let's look at an example here. An example. So if you're asked to integrate indefinite integral, so antiderivative, of cos x squared times 2x dx. That's of that form. Okay, we got f prime of g of x. That's g prime of x. And there you go. Okay, that looks like that. And so the antiderivative, the general antiderivative is that. Ooh. Good, 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 good. Okay? All right. And if you work this thing backwards, it makes sense, right? You take the derivative of this, chain rule kicks in, you get cos of x squared times the derivative of this, 2x. Okay? So that should at least look right. So if you've got an integrand of that form, you can write the antiderivative like that. Incidentally, I gave you an example in tutorial. I wrote something like that. Essentially the same story. I use this example here to clarify some things, but that's essentially the same deal. And what else? I would just point out that cos x squared on its own, so if I just given you that, you should have slapped me, because this is one of those things that you can't write an elementary antidifferential, well, an elementary antiderivative for. Okay? Cos x squared on its own, sin x squared on its own, e to the x squared on its own, those things you can't write elementary antiderivatives for. Okay. All right, well this all makes sense, it looks like that, but there's a lot going on in the left-hand side here. This might be hard to recognize, okay? And if we've got more complicated functions, this becomes hellish, it becomes like prohibitively dizzying, so let's try to simplify things, let's try to clean this up. So we tried to clean this up with a substitution, hence the name. A substitution helps clean things up. Okay, so we let u equal gx, and this is the suspected inner function. Or inside function. Okay, this guy. Okay, so again, this works, this is true because of the chain rule. If you run this thing backward, you should be able to see what's going on. But this is hard to recognize, this pattern sometimes, or even if it's not hard to recognize, it just makes things look messy, it's upsetting. We don't want to be upset. We use the substitution, it makes things look better. Okay. So let's try the example again with a substitution. I want to leave this somehow. Okay, let's do the example again. with a substitution. Okay. So I said what? I said let u be the suspected inside function. This is our suspected inside function, okay? It's inside of something. We'll talk about other stuff shortly, but it's inside of something. It makes sense to call this our suspected inside function. So we let u equal x squared. Okay. Of course, it's disconnected now.
So I'm gonna do that second.
Remember these? We need them now. Okay. Differentials. Okay? And integrals essentially have differentials in them. So, if you remember that, you don't have to write that down, you already have that somewhere. Okay, so the differential for u is this guy's derivative times dx. Okay? Or if you want to do what I do as a memory aid, you do this. You write du over dx, the derivative of u with respect to x is 2x. So what does that tell you? It tells you that du is 2x dx. Okay? Okay, 2x dx is du. This guy is cos u. Okay, so we can write this integral as cos x squared is u. Du is 2x dx. And heck, that looks a lot nicer than before. Okay? So what have we done? Our suspected inside function we now represent by a single variable. Its derivative, which will show up because of the chain rule going the other way, its derivative gets absorbed by this differential. So everything looks a lot cleaner. Okay, what's this thing, people?
Sine.
Thank you. Sine. Okay, take the derivative of sine, you get cosine. And that's it. Our initial question was about x, so this better be in terms of x, so you substitute back this thing into this thing, and you get that. Same answer, okay? Arguably a bit nicer to look at, because you made the substitution. Again, that derivative got absorbed by this thing, you replace the function by just a single variable, everything looks nicer, it's something you can anti-differentiate, and then you substitute back in at the end.
So this gets absorbed.
Okay. When you're doing integration by substitution, it's important to remember to treat these guys, this dx, du, these kinds of things, as differentials, okay? And the substitution rule, which is what today is about, is essentially that these things can be treated as differentials. Okay, differentials like we talked about before. If you're unconvinced by that, grand, it can be proved, it takes a line, we've seen all the pieces, ask me and I'll show you, check it out. Whatever. But the lesson is, in the substitution rule, you can treat these guys as legitimate differentials. Okay, let's just write everything in here as well. This was u. This whole thing was du. And this was u. Okay, so this is just the integral of f prime u du is f at u plus c, which is a lot simpler than what it was before. Okay, it tidies things up. It's still chain rule in reverse, but it just looks nicer. Okay. You can write this down if you want. You can look it up later if you want. Basically, know the steps. You should be practicing this so the steps become internalized. You shouldn't have to look at that every time. Okay. Okay, questions about what I did so far? Okay, example. Integrate x over square root of 1 minus 4x squared. with respect to x. Okay, I'm going to be following those steps, which are essentially the steps I just did, but itemized so you have a nice recipe, and you can learn and you don't forget anything. Okay. All right. What's a good inside function here?
1 minus 4x.
Thank you. Yeah. Excellent. It looks like it's on the inside of something. Okay, that's our step 1. Okay, you come up with a decent substitution, you change your variable. Okay, so you go from x to u. Okay. Then we have to do this differential thing. Okay, the derivative of u with respect to x. Derivative constant is 0, 2 comes down, minus 8x. Good? All right. And then we can relate the differentials. Okay. Now, one way to do this is now to solve for this dx. Okay? So I'll write that. Dx equals minus du over 8x. That's one way to do this. Okay? And then you can throw that into there. Okay, so what we're going to try to do now, as we did before, is try to express this thing just in terms of u. So in terms of u and du. So here we go. Okay. So what do we got? We've got x over root 4x squared. Dx is that thing. Okay? Hey, look, something conveniently cancels. Okay? Now I'll write that. I'll pull out the constants. We're not done yet. Not everything's in terms of u. Okay? That's u there. Okay? So we'll replace this guy too. That guy's u. So I can write this as minus 1 over 8 integral of 1 over square root u du. Okay, what do we do? We suggested a substitution based on what we saw inside. We related the differentials. We plugged in to replace the dx with du. We saw that we still had some x's kicking around. That's no good. But we can replace this guy by u. And we wind up with this. Okay? And that looks a lot nicer and more doable than that did. And that's the point. We'll keep going over here. Okay, I can rewrite that as this. Minus 1 over 8, indefinite integral of u to the minus 1/2 du. You don't have to do this if you know how to anti-differentiate this directly, that's cool. Okay, people, antiderivative of this thing. Or what do I do? Yep.
Maybe 2u to the 1/2.
Good, good, good. Okay, what do you do? It's a power function, there's no minus 1 here to upset you, okay? You crank up the exponent by 1, and you divide by the new exponent. You crank up this exponent by 1 and you get 1/2. You divide by 1/2, that's like multiplying by 2. Okay, so what do we got? What did I say? 2u 1/2. Excellent. Okay, take the derivative, make sure that makes sense. Again, just power rule backward. Okay? Alright. This will get nicer. Again, the person who gave you this question didn't care about you, didn't know about you, so you better give him an answer in terms of x. Okay? So you substitute back in. Step 4 was the anti-differentiation, I believe. And step 5 is plugging back in to give whoever gave you this question an answer in terms of a variable they actually recognized. Cool? All right. And you can check this. You take the derivative of this, okay? You should be able to see chain rule working. You should be able to see that x emerge, okay? And from this, if you take the derivative, you should wind up with the integrand here. That's how you check these things. Okay. Another way to do this, instead of doing this weird business here, okay? Where do I want to write this? In a bubble. Or, okay, instead of doing it like this and plugging this in here, you could have recognized that x dx is in here, okay? And so x dx is equal to minus 1/8 of du. Okay, so again, instead of doing this and substituting for dx, what you could have done is recognize that x dx is in here, and that's what you'd love to replace, and x dx is here, and that's equal to minus 1/8 du. There we go. And then you can plug minus 1/8 du in for this, and you'll get the same result. Whatever you like. Questions? Okay. Again, that is a recipe. Know all the steps, do all the steps, practice this so it becomes part of you. Go ahead, yeah.
Yeah, what kind of level of question would this be compared to something we'd see on the exam?
For this kind of question, easy. Yeah. Substitution questions can be crazy. So, yeah, this is on the, yeah, just do it a few times and this will be piece of cake. Okay? I suppose this one was easier, but this one's still relatively good. Yeah. They could be nuts. Okay? Okay, in math, changing variable is a really, really common tool, okay? And it's a really, really handy tool. What have we done? We've made life easier by expressing stuff in terms of a different variable, okay? In this case, that might have been a bit opaque looking, okay? But if you do all this stuff, you get this thing, and that's really easy to anti-differentiate, and then all you do is you plug back in at the end. Life's good. Okay, now your question could be, how do you know what substitution to make? Okay? Experience, practice, trial and error. Okay? Probably not too much once you get a bit of experience. Okay? What were we looking for here? I said let's look for something that's on the inside. By the way, this doesn't always work for all integrals, right? This is a special class of integrals we can tackle with this rule. We were looking for something that looked like an inside function, and that was on the inside. Okay? What else is true about this thing? This guy's derivative, up to a multiplicative constant, turns up here. Okay, and that has to happen for this to work, or something like it has to happen for this to work. That's what allows this cancellation to happen. Okay, or that's what allows this substitution to make sense. Okay, so essentially this should be inside somewhere, and the derivative of this, possibly with a constant multiplied, should appear as a factor of the integrand. Good? Okay. Okay, and all you wound up having to do was essentially, you anti-differentiated the sort of derivative outside function, which hopefully made your life easier. So that final integral you get in step 3 should be quite doable. Okay? Otherwise, this method doesn't work, or your substitution was bad, you should try something else. Okay. I put these in here so you can see what's going on in symbols. You don't really have to write any of this down, frankly. Know the steps, be able to apply them. That's what you need to be able to do. Okay, I haven't written my usual formal statement of the rule because it seems boring and unfulfilling. The statement of the substitution rule is essentially that. Okay, that's the result. But that's the method you need to use. That's what you need to be able to do. And just for the record, if you like to know the conditions for these things, because we all love checking conditions, it's things like f prime and g prime continuous. And range of g an interval. Okay, it's possible for that not to happen and for the method not to work, okay? I've never in my life checked that condition, so that should tell you something about how often you'll encounter anything that isn't like this. Okay? I'm just doing that for the record, don't worry about it. Okay. Where am I? Okay. We just found this thing. On your own, if you want. Try this. I say try, I'm pretty much going to give you the answer and all the steps. The answer is going to be this. A half of arc sine 2x plus c. Okay, this is an interesting thing, okay? This looks a lot like this, and yet look at how different the answer is, okay? And in fact, you can change the question a bit and just not be able to get an elementary antiderivative at all. So little changes have big effects in these kinds of things. Okay, if you haven't got a blind clue how to do that, some tips. The derivative of arc sine is the reciprocal of the square root of 1 minus u squared. Notice in there that 4x squared is equal to 2x all squared. You can do this using my make a guess, take the derivative, correct the guess thing. You can use a substitution like that. No weird mysteries there. I've given all the pieces. That should be totally readable. Okay. Okay, on a related note, when I do stuff like this, we've done things like this before, okay? And I said, well, guess what looks reasonable, correct it with a correcting factor if you need to, and get the answer that way. And we've got a few examples in here in the tutorial like this. If that idea makes you uncomfortable, you can use a substitution here too. So for this kind of thing, you can use the substitution u equals pi x and do it that way, okay? So if my method of guess what you think it should look like, take the derivative, correct with the correcting factor is weird. Try this, it'll work, okay? Similarly, if you have something like this, you can do the guess and fix thing, or you can use this substitution. Okay, and I believe in your homework you'll see stuff like this. What's a reasonable substitution? Excellent, that's inside, yeah? There we go. And that'll be nice and neat and lovely. Okay, another way is to expand this whole thing, but that's a pain in the butt. Okay? So you can do all these things with guess and fix, but substitution works and it may be better for you now. Okay? Okay. These are different. All right. Questions at all? Okay. Guess what's next? Definite integration. By substitution. Okay, so suppose you've got a similar-ish sort of integral, but now we've got limits. Okay, so you've got a definite integral. What do? Option 1, you do this thing. Okay, you find the indefinite integral, and then what do? You evaluate the endpoints, subtract, and get your answer. Okay? So option 1, use the indefinite integral. Option 2 is to modify that method so it works for definite integrals. That's what we'll talk about now. Okay, so hoping the colors don't go nuts this time. That's for indefinite integrals, that's for definite integrals. The changes are in red. Okay, so you see there's a change step, there's a new step, and we now have limits everywhere. And here's our example. Integrate from e to e squared, the square of ln x divided by x with respect to x. Okay, again, for the record, as with a lot of these slides, you don't actually have to transcribe them. If you learn the steps, you're good enough. Or if you have an intuitive feel for stuff, you're good enough. People, what looks like a good inside thing? What looks like a substitution that's decent? Whose derivative do we see in here? Ln, that's it. I said practice and experience. For the more, tame stuff, it doesn't take that much practice. Okay, so ln looked like it was inside. Its derivative we're seeing as a factor in the integrand, and some people would say if you see something complicated or upsetting or ugly, you might want to try substituting for that thing. Okay. All right. So that was step 1. Make your substitution, or declare your substitution. Step 2 is relate the differentials. Derivative is 1 over x. Okay. So either, as before, you can sort of solve for dx, which is x du, or you write du is dx over x and you use that directly. Okay? So again, you relate the differentials. New step. We have limits now. We have to put our limits in terms of the new variable. So I call this 2.5, you can call it 2.5 if you want. Okay, our limits are e and e squared. We're going to change our variable. You got to put everything in that new language, okay? Integrand, differential, limits. Everything has to be in the new language for this to make any sense. So, x equals e. That looks like a limit, so we won't do that. Okay, when x is e, u is ln e. What's ln of e? Thank you. What's ln of e squared? Hello?
2.
Thank you. Okay. I appreciate it. Okay, so that's the new job that we have now that we didn't before. We've got limits now. We better put our limits in terms of the new variable, otherwise this isn't going to make any kind of sense. Now we rewrite the integral in terms of the new variable. Okay. Do this in as many steps as you feel you need, okay? One thing you could do is you could substitute x du in for dx. The x's will cancel, and that'll work. Or you recognize that dx over x is in here. There you go. You just replace that directly with du, whichever one you feel better about. Okay? So this guy is du. You got to put everything in terms of the new variable. The integrand, differential, and limits. Ln x was u. Okay? So far we've got u du. That's great. Everything in the sort of the meat of the integral is all in the new language.
What about the square? What about the square on the ln x squared? Would it just be useful? Yeah.
Whatever this is, you apply that function to it. So you take the ln of e squared and you get 2.
I mean, like, you know, like we did ln x is equals to u.
Oh, this thing. Yeah, because I'm just being sloppy. I'm being wrong is the answer to your question. Thank you. Very good, thank you. All right. This is a huge trap, easy to make this mistake. Do not just put e and e squared here. Again, you're talking about u, everything's got to be in terms of u, okay? And you've decided that now your new limits are 1 and 2. 1, 2. Okay, don't forget that. Really, really easy to do, okay? And this is a reminder. It says, I'm with respect to you. So these better be about you, not about x, okay? Everything's in the new world. Excellent. That looks a lot more doable than this was. I've asked you this before, so I won't ask you this time. Okay, an antiderivative of this with respect to u is u cubed over 3. Okay, so this is step 4, you antidifferentiated. Now, when you had an indefinite integral, you wanted to throw everything back into x world, okay? You don't need to do that here. All you need to do is evaluate this thing. You're in u world, your limits are in u world, you just evaluate that and you're done. Okay, you don't have to go back into x land for no reason. Okay, so just do that. 2 cubed over 3 minus 1 cubed over 3. 8 minus 1, 7 over 3. So again, the things that are different now are we have limits, and we better remember to translate those limits, and we just have to evaluate. We don't have to bring x back into the system at all. Okay? Any questions? You don't need to know this. Okay, we started this course talking about circles. And recently we had an integral we wanted to find, and we needed to integrate something that looked a bit like this. You may remember from 0 to 1. And what we did was we knew what the area of a circle with given radius is, and the thing we were looking at was a quarter of a circle, so we just did 1/4 pi r squared, and that's how we figured out what the integral was. So we used an area that we knew to find an integral. Okay? I wanted to ask, how can we do this another way? And so here's one way. You would try to go the other way. You'd use the integral to try to find the area of the circle. Okay? So here's a semicircle. Semicircle, the radius r, center is the origin, and that's the equation of the semicircular arc. Okay? Y equals this guy, which we've seen before. And if you want this area, all you need to do is integrate, definite integral from minus r to r of that function, okay? And that looks hard, and it isn't doable by the methods we know so far. And it turns out one way to deal with this kind of thing, and this is only one way to calculate this kind of thing, one way to deal with this kind of thing is to make a substitution. So like today, but a different kind of substitution. Okay, if we sub in x equals r sine theta, this becomes very nice. Okay, and you'll get, what, a half pi r squared. Okay, so you make that substitution, do a bit of work, use an identity, I think, and you'll get there. If you want to try this, talk to me about it, go for it. There's nothing that you need that you haven't learned. Okay, we know everything for this. And this is in 128 as well, and it's called trigonometric substitution, in case you're interested. Okay, I'm going to do one more example. Questions? All right, one more example. Okay, this is indefinite, okay? So not this, this is just a disembodied example. Okay, I want an antiderivative of tangent. I offhand do not know an antiderivative of tangent. I don't remember anything we saw that gave us this derivative, okay? And if you do, brilliant, tell me. I don't, right? So it's not simple, and when it's not simple, you know, try something else. Something that sometimes helps with integrals is identities. And this is the simplest identity. It's the defining identity for tan. It's this. What's a good substitution? Cos is a great substitution. Okay? It's in the inside of a reciprocal. Its derivative is sort of showing up here. That's a good substitution. Okay? Did I number everything? Almost. I didn't number this. Okay. Okay, so we make that substitution. Okay? The derivative is minus sine. Don't forget the minus sign. Okay, however you want to do this. So you get minus du is sine x dx. Well, that's nice. Okay, so if you'll pardon my laziness here, that integral is equal to sine x dx gets replaced by minus du. Cos x was u. Hey, that looks familiar. And I'll bring this minus sign out to make this look more reasonable. Again, sine x dx was du, or you can do that solve for dx thing and plug that in. Cos x was u, we throw that down there. And there we go. What's an antiderivative of this thing? Ln. What do we have here? We have minus ln absolute u plus c. That looked simple. That was cryptic. Okay? Okay, what do? We're in U world. The question was in X world. Translate back. Minus ln, what was U? Cos. That's it, that's the answer. Which maybe you could guess, if you're that kind of person. Incidentally, for the record, last thing I'm going to write. This is a log. This is non-negative. You could bring this minus up here. Minus 1. A reciprocal of cos is called secant. You could write that as ln absolute secant x plus c. If you really felt like it. That's it. If you have any questions, ask. Office hours today, projects due Friday, assignments due Monday. Next class we'll talk about areas between curves, and that's our last real lecture. Thank you, everyone.